Hello, calculus. We're going to look at another optimization problem today, and it is probably the 8th. So you're watching this after Thursday's class. All right, here's the situation. Let's zoom in a little bit. All right, optimization. I have a page. It's a printed page, and the page has 24 square inches of print on it. So imagine that. So I have a page, and the print, all the print on the page occupies this area right here, and it's 24 square inches of print. The margins at the top and the bottom are 1.5 inches. And the margins on the left and the right are 1 inch. So these margins are set and cannot be changed, but the configuration of the print here can be changed, so I can have a really long, skinny print part like that. And I would, to have that, then the page itself would be skinnier and longer, something like that. So I can have the dimensions of this page, so this times this, to be anything, but I've got to keep the print square inch values 24, and the margins are set. But the actual page can have other dimensions, any dimensions. So that's what I'm trying to think about here. So let's find the page size so that the least amount of paper is used. So we're going to find the page size that keeps these requirements, 24 square inches of print, these margins, but I want the page size. When I say size, I want the dimensions so that I'm using the least amount of paper. So to do that, let's look at what is known. If we call, let me redraw this page. So here's the printed part, the 24 square inches. Let's say that the dimensions of that, let's say this value is X, this from here to here, and this value is Y. All right, it doesn't matter which I call X or Y. So if that's X and that's Y, how shall then, to get the dimensions of the whole page, when we finally get X and Y, we would add, since there's 1.5 inches here and 1.5 inches here, to get the dimensions of the page, we're going to add 3 to Y, and because the dimensions, the margins in this direction are 1 and 1, we would add 2 to X to actually get the dimensions of the page. So in the ends, we do want this dimension and this dimension. All right, so why didn't I put the X out here and the Y out here? Just because I'm told that the printed part is 24 square inches. So that leads me to a statement, X times Y equals 24. So that kind of simplifies that. So I'm going to start with that statement, but the statement that is most important is what I'm going to try to minimize. I see the word least amount of paper. So what I'm trying to minimize is these outer dimensions. So that would be X plus 2. I'm adding the margins to the X direction, and Y plus 3. and that will be the area of my entire page. So let's go with that, and again, as yesterday, find the formula that relates the object that you're looking for. So we're looking for the least amount of paper, or area of paper. So I found the general equation. So that's what I'm going to find the first derivative of and minimize by setting it equal to 0. But the first thing first is we want to work in one variable, not two. So I'm going to be able to replace y in terms of x by the use of this statement. So when I have that statement, I'm going to rethink that, so I can say y equals 24 over x. So every time there's a y, I'll put in 24 over x. Alright, so before I take the derivative, I'm just going to distribute this out. So x times 24 over x, x times 3, that becomes 48 over x, and this becomes 6. Alright, 24 and 6 are 30, plus 3x, plus, say, 48, x to the minus 1. So, find the derivative. Sweet, we don't usually have such simple derivatives, first derivatives lately. So, we can relax a little bit. And that is 3 minus 48 over x squared. Alright, so I found the first derivative. I'm going to set that equal to 0. Clean it up by multiplying through by x squared. Alright, divide both sides, we'll divide everything by 3. Solve for x. X equals plus or minus 4. And it doesn't make any sense to have a dimension of negative 4. So I'm going to just stick with the positive 4. So first we need to see if that's a max or minimum. So looking on our first derivative line, if I'm testing 4, I'm going to test something on this side and something on that side. So testing 3, I put 3 into the first derivative, which is right here. And I get 3 minus 48 over 9. And that causes me to have a value that is negative. And on this side, when I put in 5, I get 3 minus 48 over 25. And that is a positive value. So that means the slope is negative, and at this point it zeroes out and then becomes positive. So we have, by the first derivative test, we have a minimum. So that's what we wanted. So what are the dimensions? Well, we know x is 4, and we have a relationship here where we have x times y equals 24. So that'll help us find our y dimension. X times y equals 24. So we know x to be 4. So y equals 6. So, looking back at how I set up my page, I now know this is x. So x is my 4 and y is my 6. So to get the dimensions of the page, to the 4 I have to add those two margins, one on each side. So it gives me 6 inches along this dimension, and 6, this dimension is 6, the printed page, 1.5 and a 1.5, that's 3. So I end up with a page that is 6 inches by 9 inches. Alright, so That's how we do an optimization problem where we're looking for the least amount. There's no difference than when we're looking for the most, except when we do this first derivative test, we're looking for a minimum, and hopefully that's what shows up in our work. All right, so short and sweet tonight, and I hope that you are having or will soon have success on optimization. Bye.